It's basically like having a new set of eyes to view the world.
Patience is very important here. We never lost hope. There were many detours, lots of heart attacks on the way.
We're all made out of these atoms, and we want to understand where they came from because it tells us something about where we came from.
Hello, everyone, and welcome to The Sound of Science, the podcast highlighting the voices behind the breakthroughs at Oak Ridge National Laboratory.
We are your hosts, Morgan McCorkle
and Jenny Woodbury. When the universe was formed billions and billions of years ago, the building blocks of life were forged with it.
Hydrogen, carbon, iron, nitrogen, calcium, oxygen are just a few of the elements born from the cosmos that make up life on Earth, plants, animals, and humans.
Renowned astrophysicist Carl Sagan once said, "We are all star stuff," because the elements in our own bodies can be traced back to the founding of the universe.
We use the periodic table to organize and understand all these elements, as they are the basis for everything in our world.
There are currently 118 elements on the periodic table. 92 of these are naturally occurring, meaning they originated with the formation of the universe. The other 26 are man-made, produced in laboratory experiments involving nuclear reactions.
As straightforward as the periodic table seems, it contains a lot of mysteries. Each element is determined by the number of protons, or positively charged particles in its nucleus. But the number of neutrons, neutral particles also located in the nucleus, can vary, forming what are called isotopes of the same element.
Scientists have cataloged more than 3,000 known isotopes and speculate there are thousands more yet to be discovered.
The Facility for Rare Isotope Beams, also known as FRIB, has come online at Michigan State University to help researchers in their quest to create new isotopes and study their exotic behavior.
FRIB has been years in the making. In fact, several of the instruments and detectors used originated from a historic facility at Oak Ridge National Laboratory.
We talked to several scientists who have been along for the journey about the history and future of this new facility and what it means for science and society.
3, 2, 1,
Energy Secretary Jennifer Granholm and MSU President Samuel Stanley officially opened FRIB on May 2, 2022, making it the newest U.S. Department of Energy Office of Science user facility.
DOE user facilities give scientists from around the globe the opportunity to use state-of-the-art tools like supercomputers, research reactors, light sources, and more to advance scientific discovery.
FRIB joins this lineup as a powerful particle accelerator capable of creating the rare isotopes we mentioned earlier.
FRIB hosts now the most powerful heavy ion accelerator in the world. And thanks to the beams from FRIB, over 1,000 new rare isotopes will be created. Those isotopes do not exist in nature because they are radioactive, they decay, but those isotopes, they are very important for our understanding of what is happening on Earth, what is happening in cosmos. They're also important for various societal applications.
That's Vitek Nazarevich. He is FRIB's chief scientist and is a John Hanna Distinguished Professor of Physics at MSU.
Vitek and his colleagues in the nuclear physics community have waited a long time to see FRIB become a reality.
If you think about it, the first ideas were in 1989, 33 years. Lots of convincing had to be done to convince our colleagues, scientists and nuclear physicists, because the amount of funds is always very limited. So patience is very important here. Okay. We never lost hope. There were many detours, many roller coasters on this path to FRIB. Lots of heart attacks right on the way.
While there were challenges along the way, FRIB is finally online and is enabling scientists to explore the field of nuclear physics like never before.
So just how do you create cosmic isotopes on Earth?
At FRIB, the process starts with a heavy ion beam, traveling at more than half the speed of light through a 1,600-foot paperclip-shaped linear accelerator. When the beam reaches the end of the accelerator, it strikes a rotating graphite target, setting off a nuclear reaction.
It basically shatters the nucleus and creates basically a cocktail of many different residual nuclei, many of which are unstable and very exotic, normally only seen in the universe and astrophysical phenomena like supernova and neutron star mergers. And this cocktail of unstable nuclei can then be separated in this long device that basically filters out the isotopes of interest and can then deliver it to an experimental end station that has a suite of detectors. And so FRIB will provide us unprecedented access to these exotic nuclei.
That's Mitch Allman. He's a physicist at ORNL who studies low-energy nuclear structure.
The instruments at FRIB will help scientists make discoveries about the properties of rare isotopes, nuclear astrophysics, fundamental interactions, and applications for our everyday lives.
Mitch is the project manager for one of those instruments known as the FRIB Decay Station Initiator, or FDSI.
FDSI is basically a collection of detectors that is extremely sensitive to rare isotope decay signatures.
And so we wanted to maximize the scientific output and opportunities. So to do so, we decided that what we needed was this FRIB Decay Station Initiator. It's a mechanical infrastructure that's designed in a way to provide this integration of all the community detectors into a single platform and ecosystem.
FDSI has a unique design that allows scientists to quickly mix and couple detectors to capture different types of nuclear data.
We also wanted to be able to reconfigure these resources quickly without losing beam time or spending too much of our time with having to basically construct and reconstruct and deconstruct and all that. So it has a reconfigurable infrastructure to where we can do multiple different measurements that might require a different ensemble of detector types. So it gives us many different ways that we can combine detectors to answer different questions efficiently.
While FDSI is new to FRIB, it and several other instruments at the facility grew out of pioneering work at ORNL to create beams of radioactive ions. This research was done at the Holyfield Radioactive Ion Beam facility.
The former DOE user facility once gave scientists access to high-quality beams of 200 rare isotopes.
Robert Zivich, a University of Tennessee physics professor who holds a joint appointment at ORNL, spent many years at Holyfield and was part of the research that laid the foundation for FDSI.
And this is a collaborative endeavor which includes many detectors from multiple labs to put in a sort of unified infrastructure. It does have a Holyfield origin because if you look into the instrumentation, there's plenty of instruments which were developed at the kind of end of Holyfield. And so they were used, you can recognize them to be used in the last experiments at this facility.
One of Robert's colleagues at the facility was someone you've already met in this episode.
Before joining MSU, Vitek Nazarevich was a corporate fellow at ORNL and led the Holyfield facility.
Robert and Vitek's research at Holyfield helped advance detector technology that can now be found in instruments like FDSI.
So one of the things which I believe, pioneered at Holyfield was the use of the so-called digital electronics, which, dates back to essentially the year 2000 when we first started to use it in this proton emission discovery experiment. So we kind of dived into this technology. It was very, very new and to some degree rather painful to use, but I think over about a decade, we made it really to a mature method.
While Holyfield was decommissioned in 2012, the cylindrical tower that housed the facility's vertical linear accelerator has become an iconic piece of the lab's landscape, and the technology pioneered there lives on at FRIB.
Robert developed a new instrument for FRIB that is used in tandem with FDSI, called the Versatile Array of Neutron Detectors at Low Energy, or VANDEL. It provides energy information about neutrons.
FDSI VANDEL was part of the first experiment run at FRIB, which was led by Lawrence Berkeley National Lab with collaborators from ORNL and the University of Tennessee, Knoxville.
The team used a variety of sensitive detectors to make measurements of survival times for 5 exotic isotopes.
And so this very first paper is more or less the question of how long do they live. And so we, in the first paper, published the half-lives which the half-life is essentially the time it takes for an ensemble to decay by half. So if I had 100 of them, how long would it take before I only had 50 of them? And so that's kind of a simple definition of a half-life. And so in this paper, we reported 5 new half-lives for the first time that weren't known before. And of course, the half-lives in themselves are interesting because it does challenge state-of-the-art nuclear theory, right? Because state-of-the-art nuclear theory tries to predict these half-lives. It's clear that there's still deficiencies in the theory. The theory isn't able to explain what's we experimentally observe. So there's still room to improve the theory and improve the physics input to how these systems are formed and how they fall apart or decay into something else.
This initial publication is only the beginning for Mitch and his colleagues. The team already has a second paper in the works that further analyzes the results from FDSI Vandal.
These 5 new half-lives and then, of course, confirming the previous half-lives was kind of like the first step, the simplest first step that we could take to process and report the data. But then we'll have extra stages. There's already a second paper that's being developed, and then there's many more papers that will come and report things on what happened to the neutrons, how did they decay, what about all the gamma rays, what are they doing, what does it tell us about the nucleus? Does it tell us something about the shape of the nucleus? It's deformed or spherical, and various other kind of characteristics of the nucleus. So these subsequent papers will touch on some of these other topics and get a little bit more detailed in the spectroscopy that we're doing and a little bit more detailed in the theory, and of course continue the challenge theory and update theory to kind of get the physics correct. Based on the survey of the data we have taken, it's clear that the combination of FRIB and the FDSI, it's basically like having a new set of eyes to view the world. There's a lot of stuff, and it's going to take a long time to deconvolute it all and to understand it all. But it's clear that this is a significant milestone and achievement, and there'll be a lot more to come.
In addition to basic laws of physics, scientists are using FRIB to gain new insight into stellar explosions and the origin of life.
One instrument at the facility is uniquely suited to help answer these questions: the Jet Experiments in Nuclear Structure and Astrophysics, also known as Gensa.
The design of Gensa was led by Kelly Chips, a nuclear astrophysicist at ORNL.
Usually when you're looking at these reactions that are taking place in stars, a star is made up mostly of hydrogen and helium. Hydrogen and helium are gases here on Earth, and so it's not easy to kind of collect them all into one place and use them for these nuclear reactions because they're a gas and the gas wants to expand everywhere.
She and her team took this challenge into account when developing the target for the instrument.
Gensa is very cool because it uses a high pressure of that gas into a very specific nozzle. And this little nozzle basically acts like a fire hose. And it turns that gas into this really just perfect stream of very dense, but it's very localized. It stays in that one spot, just like the water coming out of a hose. So instead of spraying everywhere like a sprinkler, it's coming right out in that stream, just like a hose. And that means that it creates a perfect target for you to hit it with your radioactive ion beam and do a nuclear reaction. So without there being anything there to have to contain the gas and hold it in, like a balloon or like windows of some type, it's really just the gas, almost as dense as a solid. It's the only one in the world that is that dense.
While Gensa hasn't been involved in the initial experiments at FRIB, Kelly and her team were able to test it out using one of the ion sources at the facility.
Right before FRIB started up, we were using an ion source that provides long-lived radioisotopes. One of the nice things about this facility is that you can have a beam from the accelerator that is going to a particular end station, a particular experiment. And at the same time, you can have a beam from an ion source that's going to a different experiment. And those things can run in parallel. And that's a real boon for us because it means that you can fit more people into, a schedule than you would be able to otherwise. That gives more people the opportunity to do science.
The results from the ion source experiment yielded some interesting results. And it's just a preview of what is to come by using Gensa on the full accelerator.
So that was what we were doing with Gensa. We were running a beam of aluminum-26, which has a half-life of almost 1 million years. It's 700 and some 100,000 years. And the interesting thing about aluminum-26 is that you can see it in the galaxy. There are space-based telescopes like Integral and CompTel that can actually map aluminum-26 from its decay. It decays via a gamma ray, a very characteristic gamma ray, and they can see that in the galaxy, and they can actually pinpoint where it's coming from. So we know that it's there. 700,000 years is a long time for us, but it's a very short time frame for the life of a star. So we know that it's being actively produced in the stars, because if it was produced only when the star was born, it would all be gone by now. So understanding how the aluminum 26 is being produced and destroyed in these stellar environments is going to tell us something about that star. It's going to tell us how that star is burning, how fast it's burning, how hot it's burning, what sorts of nuclei it's producing. So that was the last thing we did, which was really cool.
FRIB will be accepting proposals for both the accelerator and the ion sources, which will allow more users to have access to the facility.
And speaking of users, Kelly not only leads the Gensa experiment, but is also chair of the FRIB user organization.
The FRIB Users Organization has existed since roughly 20 years now. The community basically came together at that point in the early 2000s and came to the conclusion that what was needed in the community was a new facility that was going to allow us to reach toward really the extremes of the nuclear chart. So all sorts of nuclei that don't exist anywhere on Earth, things that are at the limit of what is even bound, which means that past that point, all of the nucleons just start falling apart. They just can't exist together anymore. This was something that was seen as a very high priority within the community. And so the community started getting together, having town halls and white papers and meetings, formed the users organization as a group to make this a more coherent project. And then after the project itself was awarded by DOE, this was our way of making sure that the community was engaged with the project and helping to define the science goals and the kinds of equipment that we were going to need to be able to achieve those goals and the kinds of expertise that was going to be needed both on the experimental side and on the theoretical side.
The user community's executive board holds an election each year to choose its chair, and this year, that person was Kelly.
Basically, in this position, I act as a liaison between the user community and the facility management. So if users are interested in seeing something happen from a scientific standpoint, they want to see the development of a certain piece of equipment or a certain type of radioactive beam. If they have questions or concerns, that kind of comes to me, and then I come to the FRIB management and I say, on behalf of the users, here are these questions or here are these priorities. It's definitely not something that's for the faint of heart. It's a lot of users. The users group at the moment is just shy of 1,600. So there's a lot of community engagement, and it's really nice to see there's a lot of community engagement, but it also means that there's a lot for me to do.
It's been a little over 6 months since the facility opened, and the excitement is still palpable.
Kelly gave us some insight into what it was like to be at FRIB during the initial experiments.
We're looking to see isotopes that nobody has ever measured before. And I think that there was a lot of excitement around that. And you could tell because everyone is clustered, in the control room. You have only a couple, monitors that are showing the data as it's coming in, but there's 30 or 40 people trying to just, pack around those couple monitors and see things as they're happening. So it was really exciting. And I've never seen that many people, in that room at one time, right? Like just to see that level of excitement and everybody being just waiting with bated breath to see these events come in kind of, one at a time. And some of these things, right? Like I said, they've not been seen before, so we don't know what the half-life is. We don't know how long it lasts. We don't know how many of them we're going to see. And so, you're waiting and then you see, one point show up on the screen and then 5 minutes later, there's another point on the screen and everybody's just, oh my gosh, like there's another one. And I've been on experiments where people were so excited that they started naming the individual events. They give it like, this one is Jim and that one is Sherry and this is Janice. And yeah, it's that level of just this emotional investment in the science, which is really nice to see, right? Because it's not just a job, it's something that we care very deeply about and we love doing.
The facility may be brand new, but upgrades to the instruments and power level are already in the works. That's something Mitch Allman is particularly excited about.
There's always a little bit of a foot in the future and in the unknown, and a foot in the past, and what did you learn from before, and how can you make the current and future runs better. And of course, we're still developing phase 2 of the FDSI that'll be implemented in this next summer. And so there's a lot of things happening. We're trying to use phase 1 FDSI. We're trying to design and build phase 2 FDSI to be implemented in the summer. And we're trying to learn the various nuances of the new facility. In terms of what I'm looking forward to, I'm looking forward to the FDSI to be finished and fully implemented at the point where we can operate it, in a more routine fashion. And of course, looking forward to the facility being complete. So the facility is having to stage itself with respect to beam intensity, mostly for just kind of safety protocol reasons. So, when we began, the machine started off at 1 kilowatt of power. And so we'll be running again in the April timeframe of 2023, and I believe we'll be up to 6 kilowatts of power, and maybe by next year we'll be at 10 kilowatts of power. But ultimately, we hope to get up to 400 kilowatts of power. And so a lot of what we're really interested in needs the 400 kilowatts of power. So in terms of what, we're doing the best we can with the limited power that we have, and there's a few, niche cases here and there that we can do. That provides new physics and new results and discoveries.
And for Vitek Nazaravich, he's waited 30 years to see this facility come to fruition. And now that it's here, he knows he may have to wait a little longer until they see groundbreaking results, but it will be worth it.
The first part of the FRIB program has to be doable, right? You have to run experiments which will be successful. You have to run experiments which will result in first-class papers. Those are not the most challenging experiments which are going to be run at FRIB. We would like to start slow, so there will be decay experiments. There will be experiments related to nuclear astrophysics, right? So with time, and I hope that within a year, we'll be reaching to the extremes. There will be experiments dealing with extremely exotic nuclei. When we say extremely exotic nuclei, we mean those which have this most abnormal ratio of neutrons to protons. Nucleus is made of neutrons and protons, and normal nuclei which surround us, 286 stable nuclei around us, right? They have very specific ratios of neutrons to protons, but those exotic ones, which will be produced at FRIB, will have crazy ratios of neutrons to protons. So the stable calcium isotopes, which exist in nature, are like calcium 40 or calcium 48, 20 protons, 20 neutrons. 20 protons, 28 neutrons. But FRIB, hopefully, will take us all the way to calcium 70, which has 20 protons and 50 neutrons. A dramatic excess of neutrons over protons, right? So, and for physicists such as myself, this is an extremely exciting proposition because it will take us to atomic nuclei which have this abnormal density of neutron matter, which you can see, of course, in different conditions in neutron stars. So neutron-rich nuclei can tell us a lot about neutron stars. So I get easily excited.
And although understanding neutron stars may seem far removed from our everyday lives, Kelly Chips reminded us that the research at FRIB is helping explain who we are at the most fundamental level.
It becomes a part of a whole suite of tools that we have to really understand the basic fundamental nature of the nucleus. And from that point of view, it's really exciting because that's what we're all made out of. We're all made out of these atoms, and we want to understand where they came from because it tells us something about where we came from.
Thank you for listening to this episode of The Sound of Science.
We hope you enjoyed this episode, and please leave us a review wherever you get your podcasts.
If you want updates on the amazing science that will be coming out of FRIB, follow @FRIB Lab on Twitter or visit frib.msu.edu.
Until next time.